And so just curious, can everybody see this? Are we good? You can even put a little thumbs up right now because everybody's got perfect interaction. That's even better. All right, now, so here's how they ask this is how they ask a multiple choice question. They say find a value of a so that the function is continuous. All right. So if you're asked to find, like they say, okay, here's a function. We're going to stick a random a in there, and I want it to be continuous, meaning I need these things connected. Okay. So what does it mean to be connected? Well, it means what it means to be connected is when I plug this value in here, I'm going to get a y value, and when I plug -1 into this, I'll get a y value. When I plug -1 into this, I need it to be the same y value, so they're actually connected, right? So if I need them to be connected, so I'll plug the -1 in here, so that's 4 minus 1, so that's going to give me a 3. So I get a y value of 3 on the top. When I plug a -1 in here, well, let's see, that's a -1 squared plus 1, so I get a plus 1. That's my y value. I need this y value to equal this y value. So for this y value to equal this y value, I just set a plus 1 equal to 3, and I find out that a is equal to 2. The big idea here is, all right, I'm going to have to get off gallery mode because I'm looking at the gallery mode, and what I see is everybody sitting in their little desk, and then I'm literally in the middle walking around. So that's that's actually more of a distraction. So I'm going to put you back. I don't know if I can do large gallery. Can I do large? There we go. Perfect. Now, you do have some homework problems. You have homework problems out of the book, and the homework problems out of the book, the first couple are, they give you piecewise functions and they ask, is it continuous? It's almost exactly what the Khan Academy one. Check the breaking point, make sure the y values are the same. The second set of problems are like this. They give you a piecewise functions, but they stick some letters in and they ask for it to find a value of a. So to find a value of a, we've got to make sure our y values match up. And I'm going to say 20 years ago, this was a super common question. Over the last 15 years, they tend to ask stuff like this. And it says, find the values of k so that this is continuous. And there's a lot going on with this particular function. I'm going to kind of give you the history of the function. You've done problems like this. I know that you did problems like this because the way that we phrased the question, or the way that I phrased the question last week was, what's the limit as x approaches 4 of 2x squared minus 7x minus 4 all over x squared minus x minus 12. So we're going to talk about sort of the development of this problem. So the development of this problem actually came from this limit. And this is something I could have given you on the quiz. Could have very easily given it to you. I could have very easily given you something like this on your quiz, like compute the limit. Like you plug in, you get 0 over 0. That means you have to do more work. Yay. Now, even if I get 0 over 0, here's what I know is going to happen. If I plug in 4 and I get 0 over 0, I don't have to know anything at all about factoring, but I do know, because when I plug in 4 and I get 0 over 0, that means that this, at some point, I'm going to get the limit as x approaches 4. I'm going to get an x minus 4 on top, times some stuff, over x minus 4 on the bottom, times some stuff. Because anytime if you plug a 4 in, you get 0 over 0, that means an x minus 4 has got to cancel. If an x minus 4 has got to cancel, that means there's got to be 1 on top and 1 on the bottom. Which is handy because it lets you figure out what goes here. Right? So like if you have trouble factoring, okay, let's factor the bottom. Let's see the bottom. Let's see, that's going to give us x minus 4 and an x plus 3, so that's fine. And if that's x minus 4, well, that's going to force the other one to be, I'm thinking, a 2x plus 1. Does that work out? Let's see, minus 8x plus 1x gives us negative 7x. Yes, it does. And so this cancels, and we just found out that that's 9 over 7, and so we computed that limit. Now, right? So this is a problem I gave you last week. Okay? This is the problem I give you this week. So this is dealing with limits. This is dealing with continuity. Believe it or not, they're almost asking the exact same question. And here's what I mean by that. It all hinges as to what does this picture look like. If I gave you f of x equals this, what does it look like? Well, it's a graph, right? You could type it in your calculator. It's a graph. It's a rational function. And I really don't care that it's a rational function. But what I do care about, if I graph this, like you did in Algebra 2 and like you did in pre-cal, when you graph this, because something canceled, you got a hole. And where did we get a hole? We got a hole at 4. So I have no idea what this picture looks like, right? Well, I do. I mean, you got an asymptote here. The actual picture isn't that important. What is important is what's going on at 4. And what's going on at 4, and again, you did this in Algebra 2 and you did it in pre-cal, your teachers said graph things, but then you also had to plot the hole. And plotting the hole is, at 4, we had a hole at 9 over 7. So here's 4, and then 9 over 7, a little bit bigger than 1, we have a hole. And, the graph is doing something. Yay. I don't know what the graph's doing, I really don't care. All I know is, at 4, I've got a hole, and that hole is at a height of 9 over 7. And reasons we know that, we computed our limit. They're saying the graph is going to this particular y value. Now, what is this question asking? It says, find the values of k so that this function is continuous. Meaning, all right, we're admitting there is a hole here. We know there's a hole here. We know there's a hole at x equals 4. That's what we know. This is asking, at what y value do we need to plug a dot in so it fills in the hole? All right, does everybody kind of see that picture? This is asking, where do we put the dot so it fills in the gap? Well, that's when we go back to what we did last week. And believe it or not, you did this in pre-cal and probably in Algebra 2. You had to figure out the height of your dot, right? When you computed that limit, that's a y value, that's 9 over 7. You had to do this in pre-cal. What's the height of your dot? So this is a y value. If I want to fill in the dot, I'm going to put my dot here. Oh, now I'm done. So my value of k has to equal, was that 9 over 7? Did that make any sense? I got very long-winded. You got a super long answer for that. All right, but I'm trying to connect everything we've done to this question. Right? This whole idea of a limit, you're looking for a y value. This limit actually had a hole. Now they're sort of exploiting the fact, okay, we've got a hole, now we've got to fill it in. So what value do we plug in to fill that part in? All right? Now, next up. Okay, and if you're curious, I'm not recording your expressions, I'm still recording me, so you're Now, to be perfectly honest, I haven't worked the I can't remember if the answers are ugly on this. I'm hoping they're not, but let's talk about it. We're going to talk about this. This is very common. It was common 20 years ago. I haven't seen it in a few years, but I've given problems like this on my test. It says, find the values of a and b so that this is continuous. So they give us this piecewise function. And when I look at this, I see I've got, let's see, it's almost like I've got three pieces. And I want to make sure, when I want to make sure something's continuous, I need to make sure the y values match up. So they were pretty nice here. They already told me this y value is 4, and if I want this y value to match up, this says when I plug in -1, all right, I've got to find my particular y value. So I'm going to plug in -1 in for my x up here, and when I do that, that gives me whatever my breaking point is. So -1 squared is 1, so that's going to give me 2a. That'll give me plus 3b. So when I plug -1 into this, my y value is this thing. They're telling me my y value is 4, so if I want these to match up, I need this y value to equal this y value, so I end up with 2a plus 3b is equal to 4. All right? And then, all right, let's look at my last two equations, or last two functions. When I plug -1 into this thing in the bottom, let's see, that's going to give me a -5b plus a. That's effectively my y value. And I know this y value has to equal this y value, so I get my second equation, which is going to be -5b plus a also equals 4 because this has to equal this. And now I have my two equations and two unknowns, and we have to solve for a and b. So solve for a and b. What do I want to do? Substitution works really well. So a is equal to 4 plus 5b. Plug that into a. So 4 plus 5b plus 3b is equal to 4. So 8 plus 10b plus 3b is equal to 4. 13b is equal to -4. So b is equal to -4 over 13. Yeah, the number wasn't nice. To figure out what a is going to equal 4 plus, what is that, 5 times -4 over 13. I was hoping it'd be a nice number. It's not. So let's see, 4 minus 20 over 13, common denominator, so that's going to give me 52. Ran out of room. So I get 52 over 13 minus 20 over 13, which gives me 32 over 13. So found out that a is equal to 32 over 13 and p is equal to -4 over 13. Yay. Usually when I pick problems, I try to pick them to be a lot nicer than this. This one didn't work out that way. But you should be prepared to solve a system. But this kind of uses the same idea as like my first example, where you've got some variables and I want to make sure they match up. So you plug in, you want to make sure your y values match up. That was not pretty. All right. Next.
Mr. Alvis?
Yes.
Why is it -5b?
Because I plugged in -1.
Oh.
Good question. Because you have to replace the x. You actually have to plug the x in. All right. So you've got like three problems where there's like three sections on your homework. The first section is here's piecewise functions. Tell me if they're continuous or not. So you practice, you plug in, and make sure your y values match up. Exactly what we did yesterday. The next section is you got like 2 or 3 problems that are similar to this. Actually, they're easier than this. They only have like an a. But you have to find the value of a that makes them continuous. So you plug in your x value in one thing, get a y value at the top, y value at the bottom, set them in equations, and then that helps you solve for a. Those are the two types of where they're practicing with something that's continuous. The third thing I need to talk about today is an application of continuity. And we get our first major theorem. There are a few biggies that we're going to do throughout the year. This is the first big theorem, and I'm going to talk about it in what I'm going to call understandable terms, and then I'm going to write it down, or actually I'm going to show you what it is in all its mathematical glory. Like, what does it look like with math terms? And in math terms, it's kind of intimidating, but in sort of layman's terms, you kind of say, well, duh, that's how it works. All right. And so our thing is called, actually, here, we'll do it this way. I'll give you the full math version and then I will translate. Because sometimes math gets really intimidating. So our big function, our big theorem of the day, big theorem of the week, probably next few weeks, all right? It's called the intermediate value theorem. It's so important that when we actually use it, we use it so much, or actually not, but it gets like things that are used an awful lot that get real important, you just get to abbreviate it. So instead of saying the intermediate value theorem every time, you say IVT. And everybody knows what you're talking about, right? Anybody that's had calculus, if you say IVT, they go, oh yeah, intermediate value theorem, because it's a big deal, all right? I mean, it's, if we look at it, it sounds real official. Like, they have all of this stuff. It says, if a function y equals f of x is continuous on a closed interval, then f of x takes on every value in between f of a and f of b on that interval, all right? And then he actually goes on to say, actually I like this part, okay. So, actually, I'm going to cut some of this out. This gets way, way, way too wordy. Put it differently, I don't care about that. I would say, okay, if f of x is continuous, and there's an f of a, I should have read his. The official title of this is, I write it over. Dang it! I need some space to write. Here's my official version of the intermediate value theorem. If f is continuous on the interval AB, then, I need to talk about this symbol. There exists a magic value C so that f of C is between f of A and f of B. All right, that's my version, and I actually think that's the version that most textbooks use. All right, this seems way more complicated than it needs to be. First, I want to talk a little bit about some math symbols. Mathematicians are very efficient people. They're very practical. I love talking to math people. I understand them. And when math people 100 years ago were writing text, they needed books written, there are certain phrases that mathematicians use over and over. One of the phrases they use is something called there exist. Okay, you don't need to know this, right? This is just me talking. There's a certain phrase that just happens over and over, there exist. And they wanted, when they're writing a book, they got tired of writing there exist over and over. What they really wanted is, can we just create a special symbol for this? Well, rewind 50 or 100 years ago, the way you made text, the way you made books, the way you printed anything was typesetting. And the way typesetting works is you got this big old like grid, and somebody has all the little letters and they sort of position them, and then run ink over it, and then put the paper down. That's how they print it. Obviously now things are different, but back then that's what they did. Well, if you wanted to make a new symbol, then that requires the typesetter to create this new symbol. Well, the mathematicians were like, we don't need you to create a new symbol, let's just use an existing symbol. So what they did is they said, you've already got an E, you've got a capital E, why don't you just write that, why don't you just put it in backwards? And so that's why this little symbol, anytime you see a backwards capital E, that means there exists. Pretty practical. All right, anyway, let me translate this with a picture, because once you understand with a picture, you think, well, of course that is. Why wouldn't it? I mean, it has to be. So, pretty much every theorem or anything major we do in calculus starts off with f is continuous, because pretty much if f isn't continuous, none of this stuff works. Everything's got to be connected. When they talk about an interval, these are x values. So if we're drawing, it doesn't have to be continuous everywhere, but it does have to be continuous. Here's an x value of A, here's an x value of B. And C is somewhere, actually, there is a C, I'm going to say in the interval AB, I forgot to say. So there's a magic C. Now, here's our picture. If we've got a graph, we're going to say the graph does this. Because here's F. And so F is in between. What this intermediate value theorem says is, if you've got a dot high and you've got a dot that's low, when you connect the dots, it's going to cross. So I'm going to call this y value f of c. It's got to cross a line. So let's think about that again. If you got two dots, right? You got two dots up here, right? You got a dot here and a dot here. It's continuous, so I've got to connect the dots. When I connect the dots, it's going to have to cross a horizontal line. That's the intermediate value theorem. So this is saying, right? If f is continuous on the interval, so these are x values, there is a magic value c, right, in that interval, so that the y value of f of c, that y value is in between this y value, which is f of a, and this y value, which is f of b. That's it. And whenever you see intermediate value theorem, it's like you got a dot up here, you got a dot down here. When you connect them, it has to cross. So how do they apply that? Well, how they apply that is, this is just making sure. They ask some pretty, I'm going to call them some silly questions. So this is an example of a silly question, and let me make that a little bigger so we can, whoa, way too big, okay. So they ask questions, and the questions they ask are similar to this. So there is a positive real solution to this equation, right? I don't like that version of it. I'm going to set it equal to 0. So show that x to the 5th minus x minus 2 equals 0 has some positive real solution. Here's another way to look at this. If I give you a function, let's say I give you a function f of x is equal to x to the 5th minus x minus 2, I want to show that there is a 0. I want to find out there is a place where this crosses the x-axis. Now, notice it's not asking for the actual answer. See, if you had to do this problem in pre-cal, the only way you could do this is actually graphing, like using your calculator, or using some features using the graphing feature of your calculator, or there's some other programs you can use. But to actually find this answer is absolutely miserable, to find a 0, because I'm looking for where this thing crosses the x-axis. Well, here's what we do. The first thing I want to do is I'm going to plug in f of 0. Because that's easy. Plug in 0, I'll get negative 2. If I plug in 1, that's not going to give me what I need. I'm going to plug in 2. So when I plug in 2, well, 2 to the 5th is 32, minus a 2, minus another 2, and so I end up with 28. So I have this function, I have this ugly, ugly function. I know when I plug in 0, I get negative 2. When I plug in 2, I get positive 28. Now, if I were to draw a picture, if I were just to sort of draw a picture with what I've got, I'd go through here and I'd say, all right, at 0, I'm at negative 2. So here, 0, I'm at negative 2. So I get a dot. At 2, I'm at positive 28. Here's 2, and I'm at positive 28, which is way up here. Can we agree that this polynomial is continuous? Everybody okay with that part? Right? It's polynomial, it's continuous. That means I've got to connect the dots. Now, what we're trying to show is that this graph crosses the x-axis, because that's what a 0 is, where it is crosses the x-axis. Now, in your, granted, you may be unprofessional mathematicians, but we're gonna change that. In your unprofessional view, if I connect those two dots, am I going to cross the x-axis? Do I have to cross the x-axis? More importantly, do I have to cross the x-axis between here and here? Like, I challenge you, there is, like, if I give you a dot here and a dot here, and I say connect them, you got to connect them with a function. At some point, it's going to cross, right? So intuitively, that's the intermediate value theorem. See, the intermediate value theorem says if you got a y value below what you're interested in, and you have a y value above where you're interested in, when you connect the dots, it's got to cross that particular y value. So if I were to cross this, right, it's going to cross. And where it crosses is that magic value c. Now, here's how we say all this. And you don't have to say all of this. Actually, we will have to, which gets to be a bit of a pain. How we say all of this, and, I need more board space. We establish that f of 0 is equal to negative 2, and f of 2 is equal to 28. We say f is continuous. So by the intermediate value theorem, there exists a magic value c so that f of c is equal to 0, which is what this picture says. There's got to be a place where it crosses. All right? That one's a pain. I wanted to do this one because this I thought was actually kind of interesting. So this is, he modified, this was a free response question from, I'm getting old because I don't think 2007 was that long ago, but it now is. All right. Typically one of the free response questions has a chart of values. So here's a chart of values. Don't worry about this little apostrophe thing. We're going to talk about that later. What I do care about is this is values of f, these are values of g. And they say that you're told that f and g are continuous, so everything's connected. The table above gives values, and they start giving us, all of this. Function h is given by this ugly thing, and explain why there must be a value r between 1 and 3, such that h of r is equal to negative 5. Well, how we approach this, anytime they say explain why there has to be a value. This is code for we're going to use the intermediate value theorem. So if I want to establish that there's got to be some place that h of r is equal to -5, these are my x values. I need to compute what h of 1 is, and I need to compute what h of 3 is. So if h of 1 is this thing, so that's f of g of 1 minus 6, and h of 3 is going to be f of g of 3 minus 6. So when I look at my chart, let's see, g of 1 is 2, and then f of 2 is 9. 9 minus 6, that gives me 3. And if I plug in 3, well, let's see, g of 3 is 4. And then f of 4 is -1. All right, so, 1. So -1, yeah. That's -1. -1 minus 6 gives us -7. So if I look at this, it tells me I've computed h of 1 is equal to 3, and I've computed that h of 3 is equal to -7. Now imagine you plotted a point. If you plotted a point, let me do this real quick. Imagine you were trying to graph h. If I were trying to graph h, at 1, I'm at 3, and at 3, I'm down at -7. And since f and g are continuous, if I combine them, they're continuous. I've got to connect the dots. And this is asking, is there a place where my y value is -5? If I look at this picture, am I guaranteed there's a place where my y value is -5? Right? So another way of thinking of that is, here's -5. That's this little horizontal line. Is there a place where you're guaranteed where it's going to cross that line? And of course, the challenge is, if you got a dot, you got a dot above, you got a dot below. Once you establish it's continuous, it has to cross. And this is how they ask that type of question. All right? All right. So I'm just curious. Those of you that turned your camera on, was it painful? It helped me out tremendously to actually see faces. Right?
No, it was fine for me.
Okay. I mean, hopefully, actually, the person who said it was fine for you, your camera's not on, but that's okay. It actually helps me out. Believe it or not, I like explaining math. I really like explaining math, but it's incredibly boring to try to teach to an empty classroom, which is what happens when all I see are black squares. It also, one thing I do when I teach is I'm looking at expressions. If I see everybody's clueless, then I know I didn't explain things particularly well. And then I think it's easier for someone to do a little thumbs up, thumbs down, or you can even do a little raise your hand and say help. And if I've got this screen where I'm seeing everybody, then it makes it easier for me to deal with it. It makes me easier to answer the question. And I mean, I've tried pretty hard to create what a regular classroom is for me. How many of your any other teachers teaching on the board? Are most people still writing on a document camera?
Mr. Jocham does the board sometimes, so that's pretty much it.
Okay. So I need a board. I'm only using about half the board space, so I'm having to squeeze things in. So summary of today. We talked about sort of the algebra questions that you can ask with continuity. If you've got a piecewise function, check the y values at the breaking point. If they're the same, then it's connected. If they're not the same, then it's not continuous. When they say find the value of a, you have to set things equal so that everything meets up. Then there's this whole idea of the intermediate value theorem, and pretty much what you do for the intermediate value theorem, at least the problems I've assigned, they give you a function, they give you an interval. So it's kind of like you don't have to interpret what I did up here. They give you a function, so like they would give you the function f of x is equal to x to the fifth minus x minus 2, and they give you an interval. So in this case, 0 to 2. And they'll say, show that it crosses the x-axis. So you plug 0 in, you get a number. You plug 2 in, you get a number. You want to make sure one's positive, one's negative, and then you can say by the intermediate value theorem it has to cross. So if something's continuous, we can say basically you're connecting the dots. Questions? Any questions? Are we good?
Is the homework on OneNote?
The homework's in OneNote. Whoops, I can stop this.